Today we're going to review rotational motion, talk a little bit about centripetal acceleration, and then talk about universal law of gravitation. So as we've seen before, if you're moving on a circle and you're rotating around an origin, in this case the origin is point 0, and the circle is given by the blue circle. Let's say you move from a position A to a position B. The angle that you move can be given by delta theta. The displacement of that particle from moving from part A to part B is just given by the radius of the motion times delta theta, as long as you measure delta theta in radians. And this displacement is delta S. Remember that if you move 360 degrees, that's equal to 2 pi radians. And we should be measuring all of our angles in radians in order to have a direct one-to-one comparison between delta theta and delta S. We've talked about rotational motion, so if you can move along a circle over time, let's say you move a delta theta in a time delta t, then you have an angular velocity omega, which is delta theta over delta t. Likewise, if you're accelerating in a circle, you can have a change in that omega, which will over that time, which will give you an alpha. If your angular velocity is omega, which is defined as delta theta over delta t, and you move one full rotation, then you can say that the time it takes you to move that full rotation is called capital T, the period of that rotation. So we have another definition for omega, which is 2 pi over t, the period. This might come in handy later on when we talk more about oscillators, since when you move in a circle, you are actually oscillating around in that circle. So as we just discussed, you can move a distance, r delta theta, around a circle, and as you move that way, you can see that the distance that if you move a delta theta, the distance that you've moved along the circle is r delta theta. So that means that the velocity of that point, the change in x over change in time around the circle, is actually r omega. So v is equal to r omega. That's the velocity of the point as it moves around the circle. We can also define a centripetal acceleration. Let's think about this for a second. If we start with a velocity that's pointing horizontal, the particle on the top is actually moving horizontal as it moves around the circle. But as it's moved a distance delta theta, you can see that the velocity, the speed or the magnitude of that vector hasn't changed, but the direction has changed. And we know that if you change the direction, then you must have an acceleration on the point. So what direction could that acceleration be pointing? If it was pointing parallel to the initial vector, then the vector should get shorter or longer. But if it's pointing perpendicular, the only thing that will happen is that the direction will change, but the vector will not necessarily change signs. So that means that the centripetal acceleration is either pointing into the middle of the disk or directly out from the disk. Either one of those will cause the change in direction of the vector without changing the length of the vector. In this case, the centripetal acceleration is actually pointing into the disk, and in a sense, you can think of this as like having a mass on a string that you swing around your head. When you swing a mass around your head, you're pulling in on the mass at all times to make it swing around. This type of acceleration is called centripetal acceleration. We can define centripetal acceleration to be r omega squared. Since we recently defined a velocity of the point to be r omega, we can see that that's equivalent to v squared over r. This is the acceleration that points towards the center of the rotation. It's called the centripetal force. Since it's not moving in or out in the circle, it must have a third law counterpart equal and opposite in direction, called the centrifugal force.